Welcome to lecture number 2 of module number 4. In the last lecture, we discussed about digital electronics and the importance of Boolean algebra in the solving process of a digital circuit or in analyzing a digital circuit. Further, we discussed that there are basically three logical operations which are used in order to analyze a digital circuits. Those three operations we discussed are AND operation, OR operation and NOT operation. Today we are going to realize these logical operations in terms of electronic circuits, and those electronic circuits which are used to realize these logical operations are called logic gates. In addition to these fundamental logical gates, AND gate, OR gate and NOT gate, we will also discuss about NOR gate and NAND gate, which can be realized by using these basic fundamental logical gates. Further, we will justify that, or we will show that this NAND gate and NOR gate can be used as universal gates. That means all other logical operation, logical gates can be realized using NAND gate and NOR gate. So let us discuss about digital OR gate, how to realize a OR gate using electronic circuitry. For this, let us consider two diodes D1 and D2. Now for both diode D1 and D2, their N side or N type of material, N side is connected to ground through RL, and their P side is connected to two batteries, 5-volt batteries, and there is a provision that each of these inputs A and B can be connected to either plus 5 volt or 0, and the output is taken across the load resistance RL. So in this circuitry, A and B are inputs where we have a provision to give either plus 5 volt or 0 volt, and Y is the output which we are tapping across this load resistance RL. Now the symbol for this circuit is this one, and this is the logic circuit or electronic circuit to realize OR logical operations. Now the positive voltage plus 5 volt corresponds to input 1 or high state, and the negative terminal of the battery is grounded, and hence it corresponds to low input or 0 state. Now let us discuss 4 cases. Case 1. In case 1, both A and B are given 0 input. That means they are not connected at all. They are connected to this ground. So A and B are both given 0 inputs. That means 0 volt. If A is 0 volt, B is 0 volt, the P side of both diodes D1 and D2 are 0 volts, and N side is also 0 volt as they are connected to ground through this load resistance RL. Now for both these diodes D1 and D2, their P side is also connected to 0 volt, their N side is also connected to 0 volt. Then in that case, what will happen? These two diodes will not conduct current. If we are giving 0 inputs to both A and B, then these diodes D1 and D2 will not conduct any current. And if they are not conducting any current, there will be no potential drop across this load resistance RL. If there is no current flowing in this direction, there will be no potential drop across this resistance RL. If the potential drop will not be there, then the output Y in this case will be 0. So what is the result? If both A and B are given 0 input and the diodes do not conduct current, then there will be no output across RL and hence Y will be 0. Now let us consider case 2. In case 2, suppose A is given 0, A is connected to this ground, but B is given high, means B is given plus 5 volt. Now if B is given plus 5 volt, then the P side of diode D2 is positively biased and N side of the diode D2 is negatively biased as it is connected to ground through this load resistance RL. Now in this case, A is again connected to ground and hence the P side of diode D1 is 0 and N side of diode D1 is also 0. Therefore, diode D1 is not in conducting state whereas diode D2 will be in conducting state, since diode D2 is forward biased where the P side is given plus 5 volt and N side is given 0 volt. Now if diode D2 is conducting, then current will flow from here to here. Current will flow starting from this is positive terminal, it will go in this direction, current will flow in this direction, that will go in this direction, and that will pass through this load resistance RL, and that finally it will go to ground. Now if current is flowing through this load resistance RL, then there will be a potential drop. And how much that potential drop will be? That potential drop will be exactly equal to this 5 volt minus some 0.7 volt depending upon the barrier potential of this diode D2. So approximately we can say that the potential drop across this load resistance RL will be equal to 5 volt. So we can consider that as output 1, Y equals to 1. So if A is given 0 and B is given 1, then diode D1 does not conduct current, the diode D1 does not conduct current, which is in cutoff state, but diode D2 conducts. Hence output 5 volt is available across the load resistance RL, that is Y equals to 1. Now in case 3, suppose now the diode A is given high 1 plus 5 volt and diode B is given 0. Diode A is given plus 5 volt and diode B is given 0 volt. Now in this case D1 is conducting because it is going to be forward biased, and D2 is not going to conduct because it is not biased at all, because this side is also 0 volt and this side is also 0 volt. So if diode D1 is conducting, then again current will flow from this terminal to through this direction, and that will come through RL to this ground. So current will flow through this diode D1 to the ground through the load resistance RL, and therefore there will be a potential drop across RL. That potential drop will be equal to plus 5 volt, and you are getting a output Y equals to 1. Now in case 4, input A is given plus 5 volt, input B is also given plus 5 volt. Therefore diode D1 is also going to conduct, diode D2 is also going to conduct, and if both diodes are conducting, then current will flow through the both diode, and that will flow to the ground through this load resistance RL. Therefore there will be a potential drop across RL which will be equal to plus 5 volt, and you are getting a output Y equals to 1 for this condition also. So please mark that here 0 volt is logical 0 and 5 volt is logical 1. So if we will summarize all these 4 cases through a truth table, then the truth table will be somewhat like this. When both A and B were given 0, both diodes were not conducting, the output was 0. When any one of A or B is given high plus 5 volt, that corresponding diode was conducting, and you are getting high in the output plus 5 volt, which is logical 1. And if both the diodes were given high voltage, one input, then also both of them were conducting, and you are getting 1 at the output, plus 5 volt at the output. And this is nothing but justifying the logical statement of OR operation. What was that logical statement we discussed in the last class? If A and B are two inputs, then the OR operation between them is justified or is defined by a statement, and the statement is, if any of A or B is high, then output is high, and this truth table is justifying that statement. And since this truth table is concluded from this digital circuit or electronic circuit, this electronic circuit can be said as a digital circuit or a logic gate corresponding to OR operation. Now let us discuss the digital circuit, electronic circuit, which can realize the AND logical operation. For that, this is diode D1, this is diode D2. Their positive terminal is connected to a 5V potential, 5V potential through a load resistance RL, and both A and B inputs of these diodes are also have a provision to either supply plus 5V or 0V depending upon our requirement. And here we are taking output across this load resistance RL again. Now this circuit is exactly going to show the logical AND operation, and the symbol for logical AND gate or digital AND gate is this one. Now let us discuss the cases. In case 1, both A and B are given 0 input. If both A and B are given 0 input, and then these diode D1 and D2 both will be forward biased. Why? Because the positive terminal of these diodes D1 and D2 are supplied with a high potential plus 5V, and the negative terminals are given 0V. That means both the diodes D1 and D2 will be forward biased. If both of them will be forward biased, then they will conduct current through them, and if they are conducting current through them, all of this current given by this battery will be drained through these diodes to the ground. If both the diodes are conducting current, then the potential drop across this load resistance RL will be opposite to the potential of this battery, 5V battery, and therefore the addition of those two will give you 0. That means at the output Y you are getting 0. Now in case 2, when A is given 0 and B is given plus 1, if B is given plus 5V 1, then diode D2 is not biased, forward biased, and diode D1 is forward biased. In this case also, the current will be conducted through this diode D1 to ground. If current is flowing through this diode D1, there will be a potential drop of minus 5V across RL, and the output, at the output, the potential across this terminal and ground will be equal to 0, because the potential of this battery will be exactly opposite to that potential drop across this RL. So the total potential will be 0 according to Kirchhoff's voltage law. Now in case 3, if A is given 1 and B is given 0, if A is given plus 5V and B is given 0V, then diode D2 will be conducting and diode D1 will not be conducting. And in that case also, there will be flow of current from this battery towards this diode and to the ground, and then also you will get output equal to 0. Now in a case when A and B both are given plus 5V 1, then what will happen? Both of these diodes will not conduct current. If both of them will not conduct current, there will not be current flow through this load resistance RL, and the potential of this output from this point to ground will be equal to plus 5V, and hence y will be equal to 1. Now if we will try to summarize these outcomes through a truth table, the outcomes will be like this. When both a and b were 0, then the output was 0. When any one of them is 0, then also output was 0, and when both of them were 1, then only the output was 1. And this truth table is representing the logical statement of AND operation, which says that output will be equal to 1 when a and b both will be equal to 1. That is the logical statement of AND operation, and this truth table is justifying that logical statement. Now since this truth table has been arrived from this digital circuit, so this digital circuit is called as the logic gate for AND operation, or called as AND logic gate. Now one thing you should mark here, that you should take a notice that when both the inputs are same, the output is also same. That means when a equal to 0, b equal to 0, the output is also equal to 0. When a equal to 1, b equal to 1, the output is also equal to 1. So if both the terminals are given same input, then the output will also be same. And this is an important fact which we will be using later. So please remember that. Now in case of OR gate also, if we will see in case of OR gate, the truth table of OR gate, when both the inputs of A and B, or when both the inputs of the OR gate are same, then the output is also same. When A is 0, B is 0, output is also 0. When A is 1, B is 1, output is also 1. Okay. So in case of both AND gate and OR gate, when both the inputs are given same, then the output will also come out to be same. Now let us discuss the electronic circuit or logic gate for NOT operation, which is called as NOT gate, digital NOT gate. For that, let us consider this NPN transistor. Here we will use the switching behavior of NPN transistor to realize the NOT gate. Let us consider this NPN transistor, and this NPN transistor is biased through 2 plus 5 volt battery and through two resistances. One is called base resistance RB, one is called load resistance RL. This load resistance is used for biasing this collector terminal through this 5 volt battery, and this base resistance is used to bias this base terminal through this 5 volt battery, where we have a provision that if we want, we can give plus 5 volt or 0 volt or ground. That provision is there in the input, and the emitter terminal is directly connected to the ground, and we are taking the output, we are tapping the output from the collector terminal to the ground. Here we are tapping the output. Now this is the NOT gate, and the symbol for NOT gate is this one, triangle, and out at the tip of the triangle there is a circle, small circle. So let us discuss the cases. Now case 1, if A is given 0 input, suppose this A is given 0 input. Now if A is given 0 input, then this emitter terminal is also 0 input. If A is given 0 input, then base is at 0 potential. This emitter is also at 0 potential connected to ground. Therefore this junction, base to emitter junction, is not forward biased. If this is not forward biased, it will not conduct any current. If there will be no current, no base current, then there will be no collector current. Okay. If A terminal is given 0 input, base will be at 0 potential, 0 volt, and emitter is also at 0 volt. Therefore base to emitter PN junction is not forward biased, and hence there will be no emission of electron from emitter towards the base, and there will be no electron hole recombination, and there will be no base current. If there is no base current, there will be no collector current. If it is not conducting current, then across this collector you will get same potential plus 5 volt, because it is not conducting any current, and there will be no potential drop across this load resistance RL. So for A equal to 0 input, you are getting output Y equals to 1. Now in case 2, if A is given plus 5 volt, and emitter terminal is 0 volt, then this base to emitter junction, where base is P type material and emitter is N type material, this base to emitter junction will be forward bias. If it is forward bias, then it will conduct current, and if it is conducting current, then there will be a collector current too. If there will be a collector current, then a current will pass through this load resistance RL. If there will be a current passing through this load resistance RL, there will be a potential drop across RL, which will be exactly equal and opposite to this battery plus 5 volt. Here in this battery, the current this voltage is plus 5 volt and current is flowing in this direction, so potential drop across this here will be plus and minus this 5 volt, and the total voltage across this loop according to Kirchhoff's voltage law will be equal to 0. Therefore the output will be equals to 0. So if there will be a high input, the output is becoming 0. Okay, since the transistor will be in conducting state or saturation state. Now if we will try to summarize this discussion through a truth table, then when A will be 0, output will be equal to 1, which is just complement of A, and when A will be equal to 1, then output will be 0, which is just complement of A. So this digital circuit is able to realize the logical NOT operation as evidenced by this truth table, and that is why this digital circuit is called a NOT gate, digital NOT gate. So students, now let us discuss two more logical gates, which are the extension of these fundamental logic gates. One of such gates is called NOR gate, which is nothing but a NOT gate followed by a OR gate. So this is the symbol of NOR gate, where a NOT gate, which is represented by this small circuit, is followed by a OR gate. This is the OR gate, and the total gate or the entire circuit is called a NOR gate. This is the symbol for NOR gate. Now if you want to see the circuit, as I told, NOR gate is nothing but a NOT gate followed by an OR gate. So this is the circuit of OR gate we discussed just now, and if we will put a NOT gate in front of it, this is the NOT gate, then the entire circuit will represent a NOR gate, where this A and B are inputs and this Y is the output. So if I divide the entire NOR gate into two gates, then this is the OR gate and this is the NOT gate. So the NOR gate, in case of a NOR gate, this NOT gate is followed by this OR gate. So what will be the output of this OR gate? If A and B are two inputs, then the output of this OR gate is A or B, represented by A plus B. Now this A or B, represented by A plus B, is input to this NOT gate. Since NOT gate has only one input, therefore the output of this OR gate is directly fed to the NOT gate, and the output of the complete NOT gate or output of this NOT gate will be equal to complement of this output of this OR gate. Now if we try to write the truth table, the 4 different combinations of A and B will be 0 0 0 1 1 0 1 1. Now the output of OR gate at this stage, the output will be, if both are 0 then it is 0, if any one of them is 1 then the output is 1, and if both are 1 then also output is 1. Now if I apply a NOT operation to this output A plus B, then the final output at Y, final output at this point which is Y, can be written as Y will be equal to 1 when both are 0, and Y will be equal to 0 in all other cases. Since the complement of 0 will be equal to 1, complement of 1 will be equal to 0, therefore the output of NOR gate will be equal to 1 when both the inputs are 0, and output of NOT gate will be equal to 0 when any one of the inputs is 1. So this is the truth table for a NOR gate. Similar to this, another gate is there which is called a NAND gate. So NAND gate is nothing but a NOT gate followed by a AND gate, and this is the symbol for NAND gate, where this is the NOT gate, symbol for NOT gate, which is a small bubble or small circle, and is followed by a AND gate. This is the AND gate, and the circuit is somewhat like this. This is the AND gate which is following the NOT gate. So NAND gate is a gate where a NOT gate is followed by a AND gate, or a AND gate is following a NOT gate. And if I want to break the symbol breaking will be like this. This is the AND gate, and this is the output of AND gate, A and B, or A dot B, and this output of AND gate is fed to the input of NOT gate, and as a result of that the final output will be the complement of this output of AND gate. If we try to write the truth table for this, the 4 different combinations of A and B are 0 0 0 1 1 0 1 1, and the output of these two inputs at this point will be 0 0 0 and 1. That means this is the AND gate, which shows that when both of the inputs are 1, then only the output will be equals to 1. Okay, and in all other cases the output will be equal to 0. Now if I'll implement, or if I'll apply the NOT operation to this output, then the final output will be equal to 1 1 1 and 0. So in this truth table of NAND gate, when both the inputs are 1, then the output will be equal to 0, and this is the logical statement of NAND gate, and in all other cases the output will be equal to 1. Now it is said that NOR gate and NAND gate are the universal gate. Universal gate in a sense that you can realize every other logical gates using NAND gate or NOR gate. So to prove that these NOR gate and NAND gates are universal gates, we have to derive all other gates from this NAND gate and NOR gate. Now if we will be able to do that, it will be proved that NOR gate and NAND gate are universal gates, and you can realize every other logical gate using NOR gate and NAND gate. Now let us discuss how the NOR gate can be treated as a building block, or NOR gate can be treated as a universal gate. For that we have to derive all other gates from the NOR gate. First let us try NOT gate. To realize a NOT gate from the NOR gate, what we have to do, take a NOR gate. Now join both the inputs at this. Take a NOR gate and join both the inputs and give a input A. Now you know that for a OR gate, if both the inputs are same, then output will also be same. and to that y you are applying a NOT gate. That's why you are finding out the output is complement of A. That's how this NOR gate is behaving as a NOT gate. To make a NOR gate, to get a NOT gate from a NOR gate, you just have to join both the inputs together and you have to give a input, and the truth table will be like this. Now to get a OR gate from NOR gate, this is a NOR gate. Okay, if A and B are two inputs to NOR gate, then the output of NOR gate will be A or B complement, or A plus B complement. Now if we'll put a NOT gate, which we get from here, this is a NOT gate which is made up of NOR gate. So we use this NOT gate here, this NOT gate here. If we use this NOT gate here, this will complement again this output A plus B bar, right? So if we'll complement this output of this NOR gate, then we will get final output as y equal to A plus B, because complement of complement is the same thing. The complement of 0 is 1 and complement of 1 is 0. So complement of complement is going to give you the same thing. So the truth table for this OR gate will be this one. If A and B are two inputs to this OR gate, then the output of OR gate will be this one. 0 for 0 0 output will be 1, for 0 1 output will be 0, for 1 0 output will be 0, for 1 1 output will be 0. This is the thing, this truth table we discussed in the last slide. Now if we'll take another complement, or if we'll apply another NOT operation to this output, then we will get 0 1 1 1, and this is nothing but the OR output. This is nothing but the output of a OR operation or OR gate with A and B as input. So this is how we can realize a OR gate using a NOR gate. Similarly, we can realize a AND gate also using a NOR gate, and the circuit diagram for that is this one. Take two NOT gate you have got from NOR gate. Take two NOR gate, join their inputs and give two different inputs A and B. That means you use two NOT gates which you have obtained from NOR gate, and output of those two NOT gates you feed it to another NOR gate. So if I write the truth table for this, now this is input A, this is input B, which are given to two NOT gates that we have realized using a NOR gate. So the output of these inputs will be A complement and B complement, which are again fed as two inputs to another NOR gate here. Now in this NOR gate, A complement and B complement are two inputs. Now if A complement and B complement are two inputs, then the output will be the OR operation, which is 1 or 1 is equal to 1, 1 or 0 is 1, 1 0 or 1 is equal to 1, and 0 or 0 is equal to 0. Now the complement of this, again there is a NOT gate, that means there will be a complement of this. Now a complement of this will be equal to 0 0 0 and 1, and this is nothing but the truth table result of a AND gate. If A and B are 0, if A and B are two given inputs, then this output is representing the AND operation. Okay, that's how we can realize a AND gate using a NOR gate. Similar to this, we can realize these three gates, NOT gate, OR gate and AND gate, using a NAND gate also. Okay, so for that, first let us derive a NOT gate using a NAND gate. This is a NAND gate. You just join two terminals or two inputs of a NAND gate and give an input, then you will get an output which is nothing but the complement of A. Since the AND operation of same inputs will be same, that means AND operation of A and A is equal to A, and after that you are using a NOT gate here, that's why the output will be A complement. So this is how we can realize a NOT gate. To realize a NOT gate, just you have to combine two inputs of a NAND gate and you have to give the input. And where if 0 is a input, the output will be 1, and if 1 is a input, then output will be 0. This is how we realize a NOT gate using a NAND gate. What we have to do? We just have to join both the inputs and you have to give both the terminals. You have to just join both the terminals and you have to give the input to that gate. Similar to NOR gate, here also you can realize OR gate using NAND gate. For that, this is one NOT gate that we have realized using a NAND gate. This is another NOT gate that we have realized using a NAND gate, and both are given two different inputs. One is A, one is B. Then obviously the output will be A complement and B complement. Those two outputs, let's feed them into another NAND gate. If both are getting fed to another NAND gate, the output will be a OR operation. Okay, the truth table for this entire circuit is this: A and B are two inputs. Their complement will be A complement and B complement, which are the outputs of these two NOT gates, which are being realized using a NAND gate. Then, and complement of 0 will be 1, complement of 1 will be 0, like that. These are the two outputs of these two gates, which are again fed to this NAND gate. So the output of this NAND gate, this AND gate, actually output of this AND gate will be A complement and B complement, which is nothing but 1, 0, 0 and 0. When both the inputs are 1, then only you are getting a output equal to 1. Now, since NAND gate is a NOT gate followed by a AND gate, so this is AND operation. We have to make a NOT operation on this. So if we are making a NOT operation on this, then this one will give you 0 and all other zeros will give you 1. So this output is nothing but the output of a OR logic gates or output of a OR operation. That's how we can assure that using this circuit and using NAND gates, we can realize the logic operation of OR gate. So let us try to realize a AND gate using NAND gate. So for that, again take a NOT gate, again take a NAND gate. The inputs to that NAND gate are A and B, and in that case the output of NAND gate will be A into B complement. Okay, now feed that to another NOT gate, which we can realize using NAND gate like this. Now if you are feeding this, then the total output will be complement of this A into B. Complement of A and B is again A and B, because complement of complement is the same thing. Complement of 1 is 0 and complement of 0 is 1. So you are getting A into B or A and B. So this is the output of a AND gate. So by using two NAND gates, we can realize a AND gate, and the truth table for this is somewhat like this. So if A and B are two inputs to this NAND gate, then the output will be A and B complement. So A and B is 0 here, whose complement is 1. If A and B are 0, then A and operation B is 0 and the complement of that is 1. So this is the output of this NAND gate, where A into B complement is coming as output 1 1 1 0. Now if you are taking another complement to this output, you will get 0 0 0 1, which is nothing but the output of a logical AND gate. Therefore, by using two NAND gates, you are able to realize a AND gate. So here we saw that by using some circuit, some little bit manipulation in the circuit, we can realize all other logical gates by using NOR gate and NAND gate. That is the reason why this NAND gate and NOR gate are called as universal gates or building blocks. So using these four modules, we are now at the end of the unit 6 of PUC to students, which is nothing but electronics, basic electronics and material, and we tried to cover almost everything. Somewhere some things are good, something maybe not that good, but I assume that if you are listening to these videos carefully, you will be able to understand many of the things. If you still think that you are not able to understand something or something is missing, you can write to me through my mail ID, and I will be trying my best to answer you. Thank you.